finally, we get to do some example problems for area between two curves. Note that this is signed area, by the way, something that I might have not said in the introductory video. When we're finding area between two curves, we're finding signed area. In other words, like, for example, when we have an area that is beneath the x-axis, that area will end up as a negative area simply because the y values beneath the x-axis are negative, and so that means that when you're adding up all the areas, which is what the integral, that's the point of the integral, adding up a lot of infinitesimally small areas, when you do that, you will get an incorrect area. Technically, it's not exactly precise because you're dealing with signed area in this case, and so negatives will make your area smaller. Negative areas will make your signed area number smaller. Anyway, here is an example problem. Area between these two curves here, f of x equals x squared and g of x equals x, from x equals 3 to x equals 5. What's always best to do before you do an area question, you don't have to do it all the time, but it's usually a good idea, is just to graph the functions, just so you have an idea what's going on. So we have our coordinate plane, makeshift coordinate plane right here, because I don't have graph paper. And so here we go. F of x equals x squared maybe looks something like that, right? That's x squared. And then we have g of x equals x, which maybe looks like, you know what? I should just use a line tool again. Here is g of x equals x, maybe. Something like this. And so, and x equals 3 to x equals 5, let's just say that that is here. Actually, let's say that is here to here. 3 to 5. So if we were to actually draw this, this is what we would see. Okay? So what we're being asked to find is the area in between those two lines. We're being asked to find this. And that's what we want to know. And we are going to find the exact area using the definite integral. And so the reason why this helps is so you can visualize the area that you're finding. That's part of the reason. And then the other reason is so you can find out what's the top curve and what's the bottom curve. Because in your integral, f of x is the top curve, g of x is the bottom curve. That's how it's supposed to be. But has it been arranged like that? Because, I mean, the function notation that we use here for, what's f of x, what's g of x, it's pretty arbitrary. So, is it going to be like that? What's going to be the top function, what's going to be the bottom function? That's going to decide how you set up the integral. And so, here we see that the top function is x squared, right? That's the top function, and that's the top function, and then your bottom function, x, here. And so, remember, the formula for finding the area of a curve is up here. And so, our area then is going to look like A equals, when you have our bottom limit, which it tells us the limit. Sometimes it's not always going to give the explicit limit like this, x equals 3 and x equals 5, and so graphing, that's another reason to graph it, so you can find out what the explicit limits are. So, but they do give us them here. So from 3 to 5 on your definite integral, f of x minus g of x means f of x meaning top function, g of x meaning bottom function. That's what f of x and g of x mean in this definite integral. It's in the yellow at the top. And so it turns out here, it happens to be that f of x is the top function actually, and g of x is the bottom function in our example problem here. And so we're going to put x squared first, and then g of x comes next, which is x. Okay, and so that's our integrand, and then you have dx at the end, and this is how you find the area of a curve. Area between two curves, actually, right here, as you see, and then it's just simple definite integral from this point on. Fundamental Theorem of Calculus, right? So, we're going to find the antiderivative, right? The antiderivative is going to be a third x squared minus x squared, a half x squared. And then you evaluate from 5 to 3. Okay, and then continue. So plug in 5, and you have a third 5 squared minus a half 5 squared minus, when you evaluate the bottom limit, which is a third 3 squared minus a half 3 squared. Cool. And so this turns out to be, okay, so it's going to be 125 over 3 minus 25 over 2. Well, that's the first part. Minus 9 minus 9 over 2. Okay, which is 175 over 6 minus 9 over 2. 74 over 3, or 24 and 2/3, 24.667, right? Okay, this is our answer. There you go. So that is the area in between the curves x squared and x from 3 to 5. There you go. It's not that bad. And another example problem, you know what I'm going to say. Why don't you take a crack at this one first, and once you have an answer, or if you just simply can't solve the problem, then you can come back. But pause the video now and try to see if you can solve the problem. Okay, so area between these two functions, sine and cosine. I wonder what curve is the top curve. I wonder what curve is the bottom curve. I don't know. Sounds like we should graph this. So let's start off by, once again, graphing. Here is our function coming up. So let's start off by plotting sine of x. Remember, sine of x starts at the origin, so it's going to look something like this, probably. Yeah, let's say that. Okay, so that is sine of x. And then you have cosine of x. Cosine of x starts at 1. Okay? So it's important to get this right. Where cosine, what the value of cosine will be at any particular value of sine. So don't just blindly draw a cosine curve here. Okay, so when we have like you gotta think about the sine of, for example, pi is equal to, if you think about it, the unit circle, the sine of pi is equal to 0. Cosine of pi is going to be equal to -1, right? Okay, so at pi, which is here, where is pi? Pi is right here, because the sine curve here is 0. The cosine curve should be -1. Okay, so it should be like this. That's a point on the cosine curve. Okay, and then how about at let's now do pi over 2. As sine of pi over 2, what is sine of pi over 2? Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Okay, so sine of pi over 2 is here, because, you can tell by the sine curve. This is where the sine curve is 1. And cosine should be 0. So the cosine point should be here. Okay. And you can go on doing this, of course. What will come after pi, because we did pi over 2. Now you would do 3 pi over 2, right? 3 pi over 2, sine is negative 1. 3 pi over 2, cosine is 0. And so here it goes back to this. And I think you have an idea. It's going to be up here this time. Cosine curve will be up there, then down there, and then after this, what point is that? Right? If this is pi, and then this is 3 pi over 2, then that is 2 pi. This is, wow, that is 1 pi over 2, well, 1 pi over 2 unit after 2 pi. Crazy. So 5 pi over 2 right there. Anyway, but you get the idea of what the curve is going to look like. And then you have another point down there. And then you'll go back up for this. And so might have spent a little too long just graphing the curve, but I think you get the idea. And so there's kind of what your cosine curve is going to look like. And by the way, that is 1. That is negative 1. Okay. This was cosine of x. Okay. So hopefully I should have helped any of you who are a little confused about graphing these two functions on the same graph. Now they're all supposed to look and correspond. And so, okay, so now we can finally get to the setting up the integral part, right? Okay, so when it comes to taking the definite, or finding the area here, which involves taking the definite integral, right? Well, first our limits, right? Our limits, they give us our limits. X equals 0, x equals pi over 6. X equals 0 is our bottom limit, right? Pi over 6, top limit. Whoops. And integrand, well, I graphed all of this, but really all that's important is 0 and pi over 6. Although for the next example, the rest of this graph might be useful. So where is pi over 6? Pi over 6 is obviously 0's here, right? 0 is here. Pi over 6 is not at pi over 2 yet, so it's before that point. Pi over 6 is like over here. The point where they intersect, the point where the two curves intersect, aka I'm talking about that is pi over 4, right? Because that's sine of pi over 4 and cosine of pi over 4 will equal each other. So pi over 6 comes before the point where they intersect. So the area we're looking for is this super narrow area where the blue curve is the top curve and that weird brownish greenish curve is the bottom curve. Why did I choose those colors? In other words, cosine is the top curve and sine is the bottom curve. The area we're finding is that green, that green space, very narrow green space. And so in that area, in that narrow space, as I said, cosine is the top curve. Cosine is the top curve, sine is the bottom curve. So our integrand then looks like cosine of x there, and then you're going to subtract from cosine, sine, dx equals, okay, and then just evaluate the integral again. Such fun, right? So integral of cosine, any derivative of cosine is sine of x, and then we got integral of sine, which is cosine. Oh, well, yeah, cosine, but So the derivative of cosine would be negative sine. So you put a negative sign out in front, which would make that positive. And so this is what you're left with the sine and the cosine. Sine x plus cosine x evaluated from pi over 6 to 0. And so it's just simple evaluation. Sine of pi over 6 plus cosine of pi over 6 minus sine of 0 plus cosine of 0. Okay. And what is that going to even simplify to? What is that going to simplify to? Sine of pi over 6, that's 1 over 2. And cosine of pi over 6 is we're at 3 over 2. Sine of 0, 0. And cosine of 0 is 1. And what does that simplify to? Negative 1 plus, we're at 3 over 2. Or 0.366, you want a decimal. Okay, and this is your answer. Okay, so that's how you do, let's try to find the area between two curves. Real problems, 2 problems right there, and there's a third problem I'd like to do, but this video is already getting kind of lengthy, so I'm going to end it here, and there will be another video for another area problem. Specifically, just like this one, except it's a little different, and it's a little more tricky. Okay, there you go.